is defined in the generality as, you have a M, a relatively open part of the boundary, okay? So M relatively open, and you minimize in omega subject to the constraint that B is bigger than equal to psi on M, and with some boundary values which we don't care much about, okay, on del omega minus M. And then we found that we have a minimizer which is harmonic. So there exists a minimizer U, which is the minimizer, such that U is harmonic here. Okay, U is harmonic here, and it satisfies because you can put up the test function one way. You will have that on this boundary del U by del mu is bigger than equal to 0, and on the set where let me draw this picture. So suppose this is the set where U equals to psi. This is something I should have done. So lambda of U is the set where U equals to psi is the coincident set, and the boundary of the coincident set is the free boundary. So it is more like a this is say the free boundary. So at least on the looking at it, right? It feels like that this is like an n-1, n-2 topological dimensional boundary, right? Because this lives in the coincidence set lives in n-1 dimensional. Boundary has to live in one lower dimension, at least philosophically. So it should be n-2 dimensional. Okay. So this is it. And on the set where U is not touching the obstacle, you can put up the test function both ways. So here you will have that on this side where U is bigger than psi, del U by del mu equals to 0. And then what we did is that we are now looking at only the case when psi equals to 0, and this M is the set where xn is equal to 0, and you are taking this omega to be V1. And I also talked about various equivalences with another version of the problem, which in the symmetric case is the same as this one. So now I have a problem where you have Laplacian equals to 0. I'm taking psi to be 0. So here you will have that U of xn or minus U xn is bigger than equal to 0. Okay, and U is bigger than equal to 0 over here with whatever boundary values. Okay, so distributionally, if I evenly reflect it, okay, all across by an even reflection, what we have is that minus Laplacian of U is 2 times, because the Neumann condition from both sides would add up, okay, of Uxn times the Hn minus 1 measure at xn equals to 0. Okay, so this is how I can write the problem, and U is bigger than equal to on xn equals to 0. Here. So because the obstacle is a 0. So now what we showed so far was that, so we saw several solutions. So we saw several examples which are like real part of xn minus 1 up to some rotation of the thin layer plus I xn. You can take mod xn to the power once you evenly reflect kappa, where kappa would be 3 by 2, 2, 7 by 2, 4, and so on. All right. And so far, what we showed was that, so at least from this example, you see that you cannot be better than C1 So, and I said that in 79, it was shown that U is in C1 alpha up to the coincidence set. So it is C1 alpha log of B1 plus closure from one side, not across. Okay. Because if there is a non-zero datum, okay, if you evenly reflect U, it sort of creates a, you see, like it changes sign. Okay. So across, if you evenly reflect, it cannot be better than just Lipschitz. But up to the coincidence set from either side, from this side or the other side, you is C1 alpha up to the thin set. Okay. So these are the two things to be distinguished. Okay. So from one side, it is this much. So this is what we showed. So we didn't follow the approach of Caffarelli, but we followed the approach of Tinderley, which exploited this complementarity condition in a very nice way of the seniority conditions. Okay. So now what we want to do is that I will state the same theorem, except for the fact that now I have more precise information on alpha. Alpha would just be half. Okay. And that would be the optimal regularity in view of the fact that when I put kappa equals to 3/2, it's still a solution. Okay. So optimal regularity. So I must mention that 79 and then 81 Kinderlehrer and then 85 Antipova and Ralseva, but then for a long while there was not much progress on the Senorini problem till 2004 in a breakthrough paper of Thanasopoulos and Caffarelli. They showed the optimal regularity C1 1/2 up to the thin set. Which way should I write view at? I think this is fine. Okay, up to the thin set, the C1 1/2, which is sharp in view of this example. All right. So, however, I'm going to follow another approach, okay, which is based on Almgren's monotonicity, which came a bit later, and it kind of simplified the previous proof. So that was around 2007 or 8, I can't remember. That is these two, along with salsa, and this is based on Almgren's monotonicity. Okay, so what is Almgren's functional? So I assume that 0, okay, is a free boundary point. Okay, 0 is a free boundary point on the thin set, and I look at this quantity n of r is r multiplied with grad u square. So what I am doing is that for this problem, I'm evenly reflecting the problem, and I would know that the harmonic the measure of the Laplacian on this thin set would add up, right? R square over br divided by integral of u square over del dr. And my claim is that if you solve something, what thing? So this starts. If you solve star and 0 is in the is a free boundary point, then n of r is monotone. So this in particular is true for harmonic functions, and this quantity, which is the Almgren's functional, was first introduced by Almgren in the context of Q-valued harmonic mass when he proved a monotonicity, and that's a big paper of Almgren. But in the context of PDEs, I mean, it has surfaced a lot, starting from the work of Garofalo and Lin on unique continuation. So that is where I think it's sort of prominence in unique continuation type problems have been fed. So it's so in particular, so what it says is that if I give you a harmonic function, harmonic in B1 without that measure, it is already known that this quantity n of r is monotone. And this in turn, it can be related to, can be proved variationally, okay, by taking the derivative, integration by parts, and using the Rayleigh-Poiseuille type of identity, which is the way the proof sort of generalizes even to variable coefficients, which was the key feature of the work of Garofalo and Lin. But just for the harmonic function, you can also get it from expanding this harmonic functions into harmonic polynomials and using the spherical harmonic. Okay, so this is connected to the logarithmic convexity of the height function. The height function, so I have to introduce it. Function which is h of r, which is 1 over r minus 1 integral of u square over del dr. So this can be related to the logarithmic convexity of this height function. That log of this hr is monotone, and this quantity, as you see, appears over there, okay, in the denominator. And this is the right scale invariant quantity. Anyhow, I mean, I would not show this Almgren's monotonicity for a harmonic function. I'll straight away go to my Senorini problem. Okay. So how do I do it? Okay. But now that I have reflected it, it becomes an interior obstacle problem. Okay. Interior thin obstacle problem. So how do I do it? So I would instead use for my computations the h of r, which is not this, but the one which is over there. Okay. So that is integral of u square over del dr. And finally, we'll see that it doesn't really matter because it is just divided by the right power. Okay. So when I take h prime of r, so what I do is that I write it in the following way. I write it as u square of r omega P1, and then I have to have this factor, right? And then when I take H prime of R, because both things have to be derivative, both this PR as well as the integrand inside, right? So this is the way where we can derivate it more conveniently. So H prime of R gives you n minus 1 R to the n minus 2 times this quantity, okay? And then the other thing would be R to the n minus 1 2u mu. And this we will write it over del BR. So in fact, what we are doing is that, I mean, you can just put it this way. So if you want to derive it in the UR, okay, and then you will have omega. But this is exactly the unit vector, right? So if I have R1, this point is R omega, the unit vector is exactly omega, right? So this is like grad U dotted with omega. Okay, so this is U mu. And then there is the R to the n minus up front. So I just again change back, and this gives me simply del BR. And then this quantity inside is U square R omega, U omega. Again, I divide by R, and I put this R to the n minus 1, and this is nothing but H of R again. Okay, so this is how you derivate this. And what? So then H prime of R n minus 1 by R H of R plus 2u mu over del BR. Right? And now sort of I write it as u square mu. Okay, 2u mu as u square mu. And then when I apply the divergence theorem to this guy, this gives me 2u Laplacian of u plus 2 grad u square over BR. Okay? And now let us understand this quantity. This quantity is supported on the, because I know that u is C1 alpha, this quantity is equal to 2 times del xn of u on the set hn minus 1 on the set where u is bigger than 0. Because on the set where, on the set where u is equal to 0, right? Because on the set where u is bigger than 0, which is to say that u is above the obstacle, the Neumann derivative is 0. So this is exactly supported on the set where u equals to 0. But since you multiply by u, so this quantity can be justified to be 0. It lives on the thin set because Laplacian u is like a lower dimensional measure, and on the set where it lives, u is equal to 0. And now thanks to the fact that I have the C1 alpha regularity, I can justify this computation. Okay? If you are utterly skeptical, you do it over an epsilon, okay? You stay away from xn equals to 0. Do it an epsilon, you will have a boundary term. Now, thanks to the C1 alpha regularity of uxn, you see, like, I mean, you will have that goes to 0 as epsilon goes to 0. So this integral can be happily ignored. And so what I have is only the gradient part, which I don't know why it is. It is 2 grad u square. Okay? And that is exactly the quantity in the top. So I will just write n of r as r dr over h of r, where d is the Dirichlet energy over a size of ball of size r. Okay? So therefore, what I have is the following, that h prime of r equals n minus 1 by r h of r, yeah, right? And then I sort of divide by hr all throughout, and then it is simply d by dr of log of h of r over r to the n minus 1, and this equals 2 dr over hr. Right? Right? But the n over there is the r up front, right? So what I put is that I put an r and I divide by r, and then what I get is that this is nothing but 2 by r n of r. Okay. Now this quantity is the right scale invariant quantity. You can just check it by change of variable. Okay, that if so that quantity is actually n r of u, right? And if you write u r of x to be u of rx, then n r of u is the same as n1 of ur. Because if I want to prove any boundedness property or monotonicity property, I better check all the scale invariances, right? In a similar spirit as what Ali was talking about in this Navier-Stokes lecture. But of course, I mean, this is much softer. Okay? So this is what you have. So now, what I want to show is that this n of r is monotone. Okay? So this is what I have for the h prime. And what I need to know is that, so I need to derivate this n. Okay? So at least I have derivated one quantity, which is h prime, okay, which is involved in the definition of n. N is RTR by HR. So now, in fact, this I should have done first, and then I should have introduced this N of R, but okay, it happened in a different order. But nevertheless, okay. So this is just telling you that how U grows, because if I take h of R by my definition over R to the n minus 1, the decay of this quantity near a free boundary point would exactly correspond to what is the decay of U, because then I will have like sub solution type estimates, okay, which I will come to later. So let's try to now compute it. So instead of showing N of R is monotone, I will show that log of N of R is monotone, because this is more convenient. So this is the same as showing. So first we have to compute n prime by n, which is the logarithmic derivative, and this equals 1 over R plus d prime R by dr minus h prime R over HR. Right? H prime has been computed, so I don't need to bother. So I just need to look at d prime of R. So what is d of R? D of R is integral of grad u square over dr. So by polar coordinates, so d prime of R is equal to integral over del dr of grad u square, because this can be written as integral from 0 to R, integral over del ds, integral over. So by fundamental theorem of calculus in one variable, you get that this is exactly this. And now what I do is that I try to apply relic to this. Okay. So now my claim is prime of R equals to n minus 2 by R d of R plus 2 u mu square over del dr. So let's evaluate this. So d prime of R on one hand I know is equal to grad u square over del dr. So I write it as x dot x by R, which is my mu. Okay, so that I can apply the divergence theorem, and then I need to normalize over here. And when I so this becomes then by divergence theorem 1 over R dr of divergence of grad u square x, right? And then what? So this would be, you take the divergence of x, that gives you n over R dr divergence of grad u square, and then let us sort of evaluate it plus 1 over R. You write it as summation of ui square, and then you derivate it with respect to j and multiply with xj. So that becomes 2 ui uij xj xj. Okay? Clear? And now what I do is that this is over here. Now what I do is that I integrate by parts this term. When I integrate by parts this term, then what happens? I put this I derivative here. So this gives me, so just this term, okay? So this gives me minus 2 by R uii uj xj, which I will write it as minus Laplacian of u grad u dot x. But now let us look at this term. Let us try to eliminate this term. What is Laplacian of u? Laplacian of u only lives on the set which is equal to uxn on the set, or 2 uxn on the set where u equals to 0 on the thin set. But when u equals to 0 on the thin set, this could just be prime x prime, right? Because this is on the thin set where xn equals to 0. So I would know that distributionally this quantity is equal to 0. Why? Because on the thin set this is equal to uxn, and this quantity, so uxn times u equals to 0 is my synonymy kind of condition. So this is also because of my C1 alpha regularity up to the thin set. This is the same as ux. This implies in particular that this times grad u prime equals to 0, right? The vector. Clear? Because on the set where u is 0, if uxn is 0, there is nothing to do on the thin set. On the set where uxn is different from 0, u has to be 0. If u is 0, then the tangential derivatives are all 0. So this quantity is 0, so I happily ignore. And the other thing that I will have is that I take this I derivative here. So that gives me minus 2 by R del ij ui uj. So that makes it like grad u square, because it only survives along the diagonal, right? Because if I take this I derivative on xj, it becomes del ij ui uj. So that is grad u square. And then I have the boundary term, which is exactly, I just leave it to you, which is 2 u mu square over del dr. Because at this point, I mean, you just have to sort of match the term, because you know how the normal is. So what it will give you is that 2 ui xi xj, and then with the right power of r, and that is exactly, so right power of r being r square, that is exactly 2u mu square over the del br. Okay, so this is the quantity here. So if I put this together, n minus 2 by r, that accounts for this, and the rest is this. And so this is, I think, all that we need to show that. So now let's put all these pieces together. So now recall, d of r, which is grad u square over dr, also has an equivalent boundary representation, which is u mu over del br. So n prime of r over n of r equals to what? It is equal to 1 over r plus h prime of r over h of r. So what is h prime of r? Over there, n minus 1 by r h of r. So that gives you plus n minus 1 by r plus 2 u mu over integral of u square del br, and from d prime r I get minus something is wrong. So 1 by r. Oh, I'm sorry. So n prime. Why am I adding this? So it's like minus. So it's 1 by r plus d prime r by d of r minus h prime of r over h of r. So I'm sorry. Why I was unmindful. Why did I add this? So this is this plus d prime r contributes n minus 2 by r plus d prime r has. So one of the term is n minus 2 by r because n minus 2 dr by dr, and the other term is 2 u mu square over del br over integral of u mu over del br. Because I'm using this boundary representation, you will realize why am I doing so, and then minus integral of u mu. So well, minus h prime of r, that is n minus 1 by r minus 2 u mu, which is again dr, because 2 dr is there in the expression of h prime r, and then you multiply by q square. So now you see that this exactly matches, as it should, because of the scale invariance. And now I'm left with that n prime by n is a quantity like this. And this can be checked to be bigger than or equal to 0 by Cauchy squared inequality. So therefore, n prime is bigger than or equal to 0 if and only if 2 times this quantity inside, which is u mu square over u mu minus u mu over integral of u square is bigger than or equal to 0, but this is exactly Cauchy squared inequality, right? Clear? Yes or no? So now the thing is that suppose u is homogeneous of degree k. Suppose u r of x equals to r to the k u of x. Then what is u mu? U mu equals to k by r u. And if you put it back here, what do you get? So if you put it back in the quantity, which is the following, I want to conclude something from here. I have shown that n is monotone, which is good, but I want to say that what are the frequencies on homogeneous functions? Okay. Remember, in the classical obstacle problem, we obtained that all blow-up limits are half-plane solutions, or eventually they are these quadratic polynomials. Of course, there are other global solutions, but they don't appear as blow-up limits. Okay, so we were able to sort of eliminate the other global solutions, at least for the purpose of regularity of the free boundary. So in a similar way, so expecting that there will be a homogeneous global limit, because finally what we want when you want to show the optimal regularity, eventually you expect that you will get over here 3 by 2 at least as one of the global. At least this is one of the likely candidates that can happen, right? At the limit. Okay. So, and nevertheless, the important thing to check is that this also shows that this quantity n is the right quantity which captures the vanishing order, right? Because for a homogeneous function, what is the vanishing order? K. Right? Why? That's K, right? So therefore, now let's put it in n of r. So therefore, n of r would be r grad u square, which is u mu divided by integral of u square, but u mu equals to k by r u. So this becomes r k u square over r cancels over integral of u square. You can cancel, this is exactly equal to k. So if u is a homogeneous function, okay, of degree k, which is the solution to the Synonym problem, then U is homogeneous of degree, then N of R is equal to K. And now I want to show the converse. Right, leave this example out. So I want to show the converse. So suppose N is identical equal to K. Okay, that means that N prime equals to 0. Okay, and so if I put equality in the Cauchy square inequality, this would not give me the conclusion right away, because at every R the constant can be different, because this happens at every R. So one cannot get overly excited. N is K means N prime is 0. If I put it back, what do I get? I get that U mu at any scale is equal to some K by R of U. And this K depends on R a priori. Now, what do I say? I put it back. So let me do it this way. Let me write it as, let me purposely write it as KR over R, so that this K depends on R. Now I put it back over here. When I put it back over here, I get that N of R, which is to be K, has to be in this case by Euler's formula, by not by Euler's formula, but by this equality in the Cauchy square inequality. This has to be U times U mu, which is KR over R times U over integral U square. So this R cancels, and this exactly shows you that this KR has to be K. So a priori you don't get that. That is so you get that. So you get a KR that comes from the equality in the Cauchy square. Then you match it back in the expression for NR, and you get that KR has to be K for all R. So you have to use the equation twice. Okay. So therefore, what do we get? So if U is a solution of the Synonym problem, then U is homogeneous of degree kappa or K if and only if N is identical equal to kappa. Okay. And this will be important for us in subsequent consideration. And so now what did we show? This N of R is monotone. Okay. And now I want to make the following claim that I will prove later, which is that N is bigger than equal to 3 by 2. Sorry. So therefore, at 0, I define the frequency limit. Right? So 0 is a free boundary point. I define N of 0 plus. N of 0. N of 0 plus. This is the free boundary limit at 0. So I put it N0. So in general, if I have x0 in the free boundary, because I can center this ball anywhere on the thin set, so x0 is on the free boundary means the xn coordinate is 0. I can center it at any free boundary point. I can likewise define the limit of this frequency at x0, because n is monotone, so it has a limit at the origin. And that origin, as you expect, should capture the vanishing order. So for a homogeneous harmonic function, or for a homogeneous solution to the Synonym problem, it captures the vanishing order. And therefore, for a general harmonic function, this N of 0 plus should correspond to the degree of the first non-zero harmonic polynomial in the Taylor expansion of U, at least for a harmonic function. So that is how it should be related to the vanishing order. Okay, so in unique continuation problems, you assume that U vanishes to infinite order, and then you show that N is bounded. So vanishing order is bounded. So that is how you solve this unique continuation problem, that if U vanishes to infinite order and N being bounded, these are like contradictory information, so U better be 0. So there cannot be non-trivial solution. It is a different thing how you prove it. Okay, but I'm just telling you that that is roughly why this quantity is the right candidate for analyzing unique continuation type problems, or to put in unique continuation type problems. And that was the first headway into these problems. First came up in the work of Garofalo and Lin. Okay, so this exists. Okay, so this exists. Now my claim is that, so at x0, N of x0 0 plus 0, let's call it kappa. My first claim is that, well, this is no longer a claim because I'm just putting the framework, kappa is bigger than equal to 3 by 2. So let's assume that kappa has been shown. The limit is always bigger than equal to 3 by 2 to show that I have the optimal regularity. So how do we show that? So now, so you just put it back. So recall the expression that h prime of r over h of r equals to n minus 1 by r plus 2 dr over h of r, right? Right? So then I do this and I write this and then I put this as n of r, right? So therefore, h prime of r, I really don't know why am I writing it again and again. So I will just write this as d by dr of log of, because h of r better be divided by the right power, right? So that this is the correct average, right? So, and this would be equal to, n 2 by r of n of r. And n is monotone, right? And the limit has to be bigger than equal to 3/2 is my, so once I assume the claim, assuming claim, which I need to give a proof, but that will be a further analysis of this problem. But prior to that, okay, so assuming this claim, I want
everywhere or everywhere.
No, this should be at any free boundary points. Let's call it kappa x naught. It's a monotone quantity, and I want to show that at every free boundary point, at every boundary of the coincidence set which lives on the thin space, this kappa of x naught, the frequency has to be bigger than equal to 3/2. Frequency means the vanishing order. Okay, and how do I apply it? So because I know that n is monotone, okay, so I can now replace it by n of x naught r, so that the balls are not centered at 0, but centered at other points on the free boundary. Okay. And then I know that this is bigger than equal to 2 times 3 by 2 r. So this will be bigger than equal to 2 times 3 by 2 r. 3 by 2. 2 by r, 3 by 2. That is 3 by r. Right? Clear? So this becomes bigger than equal to 3 by r. And now what I do is that I integrate this from r to 1. I integrate this quantity from r to 1 of log of h of r over r to the n minus 1. Well, h of t over t to the n minus 1, and then you integrate this quantity from 1 by r, 1 by t, r to 1. Okay, so this will give me h of 1 over 1 to the n minus 1, I don't care. So log of h of 1 divided by, because log of the difference, right, because this is the derivative of this. So, right, because this is d by dr of this. I forgot to write. So when I take the log of the difference, it is like log of a by b, right? So this quantity inside will be h of r over r to the n minus 1. This will be bigger than equal to 3 of log minus 3 log r, right? Because log of 1 is 0. And then when I open up the log, what do I get? So when I open up the log, what I get is that h of 1, I mean, if you want to stay away from the boundary, you take h of half, but it's a bounded quantity, okay? H of half is a bounded quantity if you want to stay away from that. h1 of h of 1 by h of r over r to the n minus 1 is bigger than equal to r to the minus 3. Okay. So then now you see a decay on h, right? So h of r is less than equal to h of r over r to the n minus 1 is less than equal to r to the 3 times h of 1 or 1 by h of 1, which I don't care, we take the constant. Okay. I think it's h of 1 because this is the denominator. So when you put it to the other side, it lives in the denominator. So this is like h of 1, which is the bound on the outer circle. Okay. So now this is enough for me because this is just telling me that integral average of u squared over del dr is less than equal to r3. And now I know that both u plus, for the same reason that uxk plus and uxk minus are subharmonic, for the same reason u plus and u minus are subharmonic. Subharmonic in the sense that it doesn't see the thin set anymore. U plus and u minus subharmonic, evenly reflected, are subharmonic across the thin set. Okay. For the same reasons as uxi plus and uxi minus are subharmonic. U itself is superharmonic, but u plus and u minus are subharmonic. Okay. So keep that certainty in mind. Subharmonic. So for subharmonic functions, I have the estimate, right? That u plus over r by 2 is less than equal to constant times in u plus over br, and then this will be less than equal to this will be less than equal to u plus u square over br 1 by 2, sorry, del br. Right? Because these are the estimates for subharmonic functions, right? U is controlled by the average value at the boundary. And then for this, I have the estimate, which is 3 times r to the 3 over 2. Because there is a 3 over here, I divide by half, it gives me 3 by 2. So therefore, what is it telling me? At every free boundary point, it decays like 3 by 2. In the classical obstacle problem, I showed you that near the free boundary, if it decays like 1 plus alpha, then the gradient is C alpha. Because outside that, I combined it with interior estimates for harmonic functions. And here it is easier, because I don't even have to subtract of an affine function. There I had to subtract of an affine function, which was dependent on the obstacle, because I took a non-zero obstacle at different points. But here it is telling me that because thanks to my situation of zero obstacle, I have that this decay estimate holds without needing to subtract any affine approximation. So now, are you convinced that at this point I can sort of leave the rest to you? Given 2 points away from this, either the distance between the 2 points are close to between the 2 points are very close compared to the distance to the boundary, then you can apply decay estimate with the interior estimate. But if the 2 points are far away compared to the distance from the free boundary, you will have a string of triangle inequalities where you can still apply this estimate. Okay. So all in all, what you get is that, so we have been able to show that U is C1 1/2. Now, modulo the fact that we have a gigantic claim, which is how in the world that this kappa is bigger than equal to 3/2. Okay. So again, for simplification, I take x naught to be 0, and I show that why that is so. Okay. So I have to show, so now I take x naught to be 0. I want to show kappa is bigger than 3/2. But for that, I need to zoom in and see what my limit is. Okay, I need to do a blow-up analysis. Okay, so in fact, what I will show is that if I will show a stronger statement, if kappa is less than 2, implies kappa has to be 3 by 2. I will show a much stronger statement than this. Okay, so that means that the points of vanishing order is either the minimal one is 3/2 or it is bigger than equal to 2. Okay, and then I will make some latest comments and as the history of this problem has had progression. Okay, so now what do? I rescale. I take the Algren type rescaling. Okay, at these points. So this was introduced by Luis Caffarelli and Salsa in this context. So what you do is that because my x naught is 0, I take UR of x to be U of R of x. And what I understand is that this integral averages, this integral average height function is like the vanishing order, right? This average height function is like the vanishing order, right? Near that point. So, because of course, there you don't get confused with the fact that it is 3 by 2. That 3 by 2 is our assumption which we are trying to prove. Okay, so now we are taking one step back. So integral of u square over del br 1 by 2. Then what do you have? By easy change of variable, you have that integral of ur square over del b1 equals to 1. Okay, and because the frequency is monotone, hence it is bounded, right? Because the frequency, and what is the other thing that you know? What you know is the following, that n of nur of 1 equals to grad of u r square over n of nur of 1, sorry. Grad of ur square over b1 equals to n of 1, which is less than infinity. N of r, which is less than infinity, right? This just follows from the scaling property. Do you want me to explain, or is it fine? Because when you square it, you divide by this, okay, and then you have that this quantity just comes out. Okay, so you 1 by r to the n minus 1, then from this r square comes out. Okay, but then because this whole integral has to be made in Rn, so you see like the powers match, a lot of good chunk of n minus 1 and r to the n cancels, and whatever is left is r, because it is a scale invariant quantity, as I said. Okay, so I will skip this computation. Clear? Because I have remarked already that it is the correct scale invariant quantity. Clear? This is believable, right?
Denominator is normalized. So
yes, so denominator is normalized. So you will see that when you change variable, there is r to the n, which has to be factored in. So when you put in r to the n, you have to divide by 1 by r to the n. Okay, so when you normalize it to BR, there will be like 1 by R to the n. This will give you R square, and the denominator is 1 by R to the n minus 1. To fill everything out, you will get that this is equal to R. Okay? So because I've shown that n of R is monotone, so it is less than infinity in a uniform way. So the energy is bounded. Integral of U square over del V1 is normalized to 1, right? And this would in particular imply that integral of U square over V1 UR square is uniformly bounded, independent of R, right? Reverse trace inequality, Hardy inequality. Okay, do anything that you want. And more, and now because of this information, so I know that U is uniformly bounded, UR is uniformly bounded in W12 of V1, independent of R, right? This is the key thing. So that is what monotone quantities do. Okay. So what monotonicity does is that, I mean, if you have a sort of a scale invariant information, and if you have some sort of pattern of how that propagates at different scales, then if you introduce this right scale quantity, which is this kind of a scaling, then you get a uniform behavior all across the scaling. Okay, which in this case is this ambient type scaling, and this is exactly the same one that is used in a slightly different form, even in unique integration type problems. In this fractional setup, and this is one special case where S equals to half. Anyhow, I won't even get into that. So it's uniformly bounded in W1. So that therefore, by the compactness of the trace operator in L2 on the boundary, this would force that integral of U0 square over del V1 is also equal to 1. So therefore, U0 is not equal to 0. This is the key thing, right? In the classical obstacle problem also, when we load things up, okay, we wanted the limit to be non-trivial, otherwise we would not be able to fetch any information. So there is a similar scenario over here too. And now if you look at all my C1 alpha estimates, and I have been rather stupid not to tell you that all the C1 alpha estimates, you can make the norm only depend on UL2. Why? Because the first norm dependent on grad U, but I know that U plus and U minus are subharmonic. And so therefore I can make the whole estimate. I can get energy estimates for grad U in terms of U. So eventually all my C1 alpha norms will only depend on UL2, but all these URs are uniformly bounded in W1 too. So this tells me by Ardella-Ascoli that up to a subsequent Rj going to 0, URj's converge to some U0 in C1 alpha. And then because what is the quantity? And then as I said, n of any, so let me write n of any rho Rj of U equals to, by rescaling, n of rho URj for rho say less than equal to half. And this is C1 alpha log, say B1 by 2. I don't care about B1, okay, in half the set. So this convergence is in half the set. The rest of the convergence is in the whole of B1, right? Because I crucially needed that the trace operator is compact, okay? So I use this to, so I use for the URs to show that U is bounded in W12, and then I went back to show that this happens. And all of this was facilitated by the fact that the energy of URs are uniformly bounded thanks to the monotonicity of this Almgren type quantity. At this point, which is qualitative, which is what we want to quantify now. So, okay, this is the scaling property. Okay, clear? Because whatever happens for U in RJ, URJ at rho happens for U in rho RJ. So this is expected, right? And now by the Almgren's monotonicity, this will go to kappa. And this I know because U converges in URJ's converges in C1 alpha. This will go to n rho of U0. So what I get is that for any rho, n rho of U0 is equal to kappa. And so that will tell me that, so this is the same as telling that U0 is homogeneous of degree kappa. And now I show my claim. Again, I bring in this scenario that a heavy arsenal of alt Caffarelli Friedman monotonicity formula. Okay, again I bring back the ACF formula. So now I want to show that kappa is, if kappa is less than 2, then kappa is exactly equal to 3 by 2. I'm sorry, I'm being a bit fast, I suppose, but it's just that, yes.
I'm sorry. So if the derivative is bounded in L2, why does that imply that the sequence cannot converge to 0, cannot converge to 0 within?
Which one?
Bounded.
So derivative is bounded in L2. These quantities are bounded.
Yes.
So integral of U square over B1 is also bounded.
Yes.
And then I use the compactness of the trace operator. So there is strong convergence of the trace operator in L2 on the boundary. The trace operator is compact from W12 to L2 on the boundary. In fact, it's even compact over a much bigger range as long as you are below the Sokolov exponents. Okay. But I just need for my matters in L2. So now I recall the Hall-Caffarelli-Friedman monotonicity. Recall ACF. And if you have the fraction of u plus minus bigger than equal to 0, u plus minus bigger than equal to 0, u plus dot u minus equals to 0, then if you look at this quantity, which is 1 by r to the 4 of grad of u plus square over mod x to the n minus 2 over br over grad u minus square over mod x to the n minus 2. I mean, this is a very weak monotonicity formula, as you know, which exploited the Friedland-Heyman inequality in a very crucial way. In fact, it is equivalent to the Friedland-Heyman inequality. Okay, this is monotone. Okay, now what I do is that I need to apply to the right candidate. Okay, so for a tangential direction E in Rn minus 1, I apply to del E of u naught plus and del E of u naught minus the limit. Okay, so along a certain subsequence. So at this point, I don't even know whether the entire sequence converges to something, but at least I know that whichever sequence goes wherever, the limit u naught has to be homogeneous of the same degree kappa. Okay, it is possible that across different subsequences, the limits are different, but they have to retain the same homogeneity because of the monotonicity of this function. Okay, and the scaling property of this Algren function primarily in this case. Okay, and also C1 alpha convergence and everything else. So just trying to fill up all the details, okay, that I just said again. So now I apply it to this quantity, and that gives me that. So now what is u naught? U naught is homogeneous of degree kappa, okay? Then del E of u naught is homogeneous at degree what? Kappa minus 1, right? So and grad E of del E of u naught plus minus would be homogeneous of degree kappa minus 2. If I put it back in the Algren functional, okay, then what I get is that phi r of del E of u plus minus, okay, plus minus, okay, shorthand, because I need to put this whole thing in, is it has to be equal to, you can check, so kappa minus 2, okay, so kappa minus 2, so that becomes r to the 4 kappa minus 2. Because it is the scale invariant quantity, right? So it has to be that. So these are the right, you divide it by the right quantity. So this has homogeneity what? 1 over mod x n minus 2, it is r to the n minus 2, r to the n minus 2, that becomes r to the 2n minus 4, r to the 4, r to n. So you see, and the ball of the measure r is rn. So r to n formally cancels. In the sense that you just check all of that, okay? And this is what you get. Now if kappa is less than 2, this goes to plus infinity, right? So this quantity cannot be monotone. So therefore, right? So therefore, if kappa is less than 2, if kappa is less than 2, then it has to happen that del E of u plus is identically equals to 0, or del E of u minus is identically equals to 0. U naught plus is identically 0, or del E of, right? Because otherwise this quantity will be, so this will be some constant, right? So therefore, this is so inconsistent, right? So therefore, in the very first place, this function has to identically vanish, right? So if this function identically vanishes, either the plus 1 has to vanish or the minus 1 has to vanish. So therefore, and this happens for every tangential direction, okay, for u naught. So now, if I forget the normal direction, okay, if I just look at the tangential direction, if I have a function f, okay, from Rn to Rn, which I will then change n to n minus 1 because u naught restricted to u naught freezing one extent, such that del E of f is either positive, is bigger than equal to 0, or less than equal to 0 for all x, then f is one dimensional. This is an exercise which is not that difficult, but let me tell you how you do it. So since I'm giving all the details, so let me push today to the end of it. Okay, so tomorrow is anyway very stressful. I wanted to finish it early, but it won't take much long. Okay, because now the regular part of the free boundary will not be as long as it was for the classical obstacle problem, because now we are using a lot of powerful arsenals. Okay, so you have to see the development of the subject. 1977, when all these monotonicity formulas were not there in their disposal, but now it's more like you said that you have a lot of new machinery in 2007. And this is pre-boundary problems is a subject where there are a lot of smart people around. You see, so a lot of new ideas kind of get incorporated. But anyway, in this context of the thin obstacle problem as well, it was Athanasopoulos and Caffarelli, and Salsa who made this groundbreaking breakthrough. Okay, well, breakthrough, groundbreaking. I think there is some repetition, but you make out what it was. Okay, so how do I prove it? How do I see this thing? So the thing is that, okay, so I look at all the keys, just that del E of f is bigger than equal to 0, but then this will imply that del of minus E of f has to be bigger than equal to 0. So it exactly has to be the subspace of directions where it's positive and subspace of directions where it's negative, and it cannot depend on any other direction, because suppose if it happens that it depends on any other direction, let this be along this, which is linearly. So I'm claiming that then this has to be the normal of this plane. Okay, normal of this. So there is a hyperplane. Such that on this side you have all the directions where del E is positive, and on this you have all the directions where del E is negative. Then my claim is that f only depends on this normal. If not, suppose it depends on some other direction without loss of that without loss of generality, I can assume that direction, along that direction, the directional derivative is positive. That means that this direction has to lie on this side of the plane. If it lies on this side of the plane, then again I draw this. Then I get that there is a set of directions where it has to be positive, but where it's negative, because it is below this plane, and vice versa for this. So it cannot be that there is another independent direction compared to this where this f depends. So f only depends on this. Is it clear? There cannot be any other plane, because these planes have to have a bad cone which is not in the good part of one, positive part of one, but in the negative part of the other. Okay, positive part of one and the positive part of the other. Okay, so whatever it is. So therefore, this f is one-dimensional. If I go back to this, this will tell me that u0 is only a function up to only u0 equals u0 of x equals to u0 of say up to a change of thin coordinates xn minus 1 xn. Okay, that is what you get, because in the thin space it is xn minus 1 for every xn. So therefore, it is a function of xn minus 1 xn. Now in 2 dimensions, if it's a homogeneous solution by using polar coordinates, sines and cosines, you can say that all the solutions are exactly that. In 2 dimensions, I told you that if you want to cook up homogeneous solutions, these are the only solutions. x1 plus ix2, where this now becomes xn minus 1 and xn to the power kappa, where kappa equals to 3 by 2, 2, and so on. So you see that the lowest frequency is 3 by 2. So if the frequency falls below 3 by 2, then what I have is that the blow-up limit is 2-dimensional. Now it doesn't say that along all frequencies it goes to the same limit. You know why? Because unlike in the classical obstacle problem, I have u on the top and some dependence on u in the bottom. So it is very much possible that even if what I'm trying to say is that even if these sequences go to the unique ones, okay, but if I do now u of Rx, so now the natural scaling would be taking u of Rx divided by r to the 3 by 2. That might not go to the unique limit, because what may happen is that you have a discontinuity on the top with respect to r, a discontinuity at the bottom, and the 2 discontinuities may just make up a continuity, okay? May just make this whole quantity continuous. So you see, like the convergence of this and the convergence of this are entirely different behaviors, okay? And this requires, of course, there have been several works on this following these works, in particular that of Petrosian, Mariana, Smith-Pega, Garcia, and Garofalo, where they were able to show even that this limit has a unique one, but that requires this Weiss's monotonicity and also epiperimetric kind of inequality, okay, which I will not get into. So this is a different issue. So we are going to stay with respect to this unpredictable scales, okay, for this process. So now we have shown the claim, right? Kappa equals to 3 by 2. Now,
you said in n equals 2, right? For n bigger than equal to 3.
So the global homogeneous solutions are not known. In the sense that, of course, these are subset of those, but whether these are all the ones, we don't know. Of course, it would be a great problem to solve if you know all these solutions, but it is the state of the art. Okay, so nothing is known beyond dimension 2. Well, something is known, but let me not get into that. Okay, at this point, rather keep some remarks if possible at the very end. Now it's already 5:30. So now I want to show that. So the free boundary has 2 parts. So what I do is that, so given the free boundary gamma, I can have gamma 3 by 2, all the points where the frequency is 3 by 2, union gamma k, where k is bigger than or equal to 2. So in fact, I don't even know all the other frequency points. There can be many. It could even be sort of very close to one another. But there have been several results and to show what are the different frequency points. Because all these limits, if you look at real part of x1 plus I to the kappa, all these can appear, right? Unlike the classical obstacle problem where everything is quadratic, here you have different homogeneities. Therefore, this Almgren's quantity, which was introduced in the, which was very much useful in the context of PTs for unique continuation type problems, was brought in as an arsenal over here. But even to do that, you see that to know that the limit is two-dimensional, they had to use this big arsenal of all Caffarelli frequent monotonicity. So the proof by any means is not at all elementary because a lot of non-trivial ingredients are all coming into play. And yeah, these are kind of major breakthroughs. I mean, there is a lot that is known about this set, but let me put it at the end. But now I want to say first is that this gamma 3 by 2, so little claim is that gamma 3 by 2 is relatively open. Open in gamma. It is the free boundary, okay? And why is this so? Now note that given any x0, this n of x0 r has a continuous behavior, right? Where x0 is on the free boundary point. And now I know that for every x0, the limit of the decreasing limit, this decreases to this kappa of x0, right? So I have a continuous function and a monotone decreasing limit of continuous function. So this function is upper semi-continuous. So if it's the upper semi-continuous and there is a gap in the frequency 3 by 2 and k bigger than equal to 2, that shows that this is a relatively open subset of the free boundary. Okay. So this x0 to kappa x0 is upper semi-continuous. Okay, it's the monotone decreasing limit of continuous function. So now it turns out that these are the points where the solution separates from the free boundary at the minimal rate, which is 3 by 2, right? And it turns out that these are the points which have some parallels with the regular set in the obstacle problem. Because at these points, I know what the limit is. So if you look at the limit, okay, so I look at one such u0, which is real part of xn minus 1 plus I xn 3 by 2, I exactly know how the zero set looks like. So I have this ball, okay, and let me draw this picture, okay, and this is the set where this is xn minus 1 positive, this is origin, and this is say xn, okay. So this is the set where the u0 is identically 0. So this is the coincidence set, this is flat, okay. So the coincidence set of u0 is the set where xn minus 1 is less than equal to 0. And now you see that this is the part where it is so flat, right? So at this point, I want to prove the regularity of the free boundary. So my regular part of the free boundary would be the points where the solution separates from the free boundary at the minimal rate, which is 3/2, right? So I want to show that so now my last claim so that I kind of put closure to this topic is I want to show that. But again, that will require some work, okay? So it is a claim which should be like a big theorem, but just a claim or a theorem, okay? That is a very big theorem. So gamma of u, gamma of 3 by 2 for my original solution is locally non-alpha. And this was also established for the first time by Luis Caffarelli and Salsa. Okay. So how do they do this? So first, let us understand how the tangential derivatives behave, right? I should not bother about xn derivative because now my free boundary is n minus 2 dimensional set. So I should only bother about the tangential directions because this is a set that lives in the set where xn equals to 0, right? So I need to compute. So given any e, okay, in Rn minus 1. So I want to compute del E of u0 and see how the behavior is. So 3 by 2 comes out, okay, and then what you get is xn minus 1 plus ixn to the power 1 by 2 with E dot En minus 1, right? Now I just look at the cone of direction. So I just look at the cone of direction C delta, where which is the set of all E such that E a unit vector in Sn minus 2 such that E, right, E dot En is say bigger than or equal to 3 by 4. I mean, this is just a very vague sort of around En minus 1, because En now gets replaced by En minus 1 because this regular free boundary lives in a lower dimensional set. At least for this solution, it is the flat n minus 2 surface, right? So now let us try to see what this implies. So when I expand this, I get this to be 3 by 2 and then square root, and then I have xn minus 1 square, the square root of xn square plus xn minus 1 square plus xn square. Right? So this is the real part. And then say this is bigger than equal to a good chunk because this is like 3 by 4, 3 by 4, 3 by 4, so 9 by some 60. Okay, on this cone. So which I call say some Cn. Okay, which is 9 by 16. It is independent of the dimension. It's a fixed constant. So I mean keep whatever you do. Okay. So now let's try to understand how this set looks like. Okay. So I know that this quantity is bigger than equal to a good constant Cn when mod of xn is bigger than equal to some gamma n. Right? So this is my picture. Okay. So now I draw this picture. And at least on this set, if I cross this, so this is my xn, this is my xn minus 1 less than equal to 0. Okay. So at least on this set, so this is the set where xn is equal to gamma n. This is the set where xn equals to minus gamma n. So on this, I have, on this boundary, I have, on this, after this, I have that this is a good number, right? And other than that, I also know that, other than that, because of this relation, I also know that in the other part of the set, I have that del E of u0 is bigger than equal to 0, right? On the other part of the set. And now how can I use this? So now since urj, let's call it uj, okay? Since uj up to the subsequence goes to u0 in C1 alpha, then for small n, for all j large, I have that del E of uj is bigger than equal to minus epsilon in this set. In this set, let's give this set a name. Let's call this set A, okay? Which is mod xn equals to this, and say this is the B1 and this is the slit, okay? So on this set, okay, on A, it is this set, and moreover, because on this it is this has a quantitative bound which is gamma n, which is Cn. So at least if epsilon is small enough, I can assume that for this, and moreover, I can assume that this is at least Cn by 2. Because if epsilon is very small compared to Cn, at least this will be Cn by 2. Agree? I mean, just take this to be half the ball, because if you are so sort of careful that you don't have convergence over P1, but from now on, I will just treat P half as B1 because I don't want to drag this 1 by 2. Okay? So at least, and moreover, you have that LE of uj will be bigger than equal to some Cn by 2. So let me call it another Cn on this part of the boundary, on mod xn equals to Cn. And now comes the thin version of Caffarelli's jump lemma. You see, if this is bigger than equal to this, this is bigger than equal to this, then in half the set, what I want to say is that in half the set, in P half, is half the set, del E of uj is positive if epsilon is small. Okay? But except for the fact that the barrier now would be of a different nature, okay? Because there it was Laplacian equals to 1, now here is a different quantity. So now is the thin version of the jump lemma. I mean, all these steps are not trivial. To even come up with the fact that this is the correct set to look at for the jump lemma, I mean, requires a very sort of a subtle and requires a lot of good thoughts in the very least.
That one is thick in extent, right? You are thickening it.
Yeah, it is thick in extent, so it is in like the full space, okay, evenly reflected.
Yeah.
But I care only about the directional derivatives which are in the tangential direction, so that doesn't change sign across xn equals to 0. Okay, so now I know that. So now what I do is the following. So jump lemma. So the jump lemma in this context will say that if epsilon is very small compared to Cn, okay, then del E of uj is bigger than equal to 0 in B half. So now what you do is that you take this H proof. So this is harmonic, right? Right? This is harmonic. So, and then in the other one, in the classical obstacle problem case, we had del E of u minus u. That was needed for the adjustment because then so that we could add a quadratic term. Here we don't have that similar luxury, but nevertheless we can do the following. So what you do is that you define this H to be del E of uj plus a little alpha that needs to be adjusted times something which is harmonic. That is, it has a positive curvature in the x prime direction. So Okay, so here is what you do in behalf. So I have to write something more. Okay, so let x naught, because it depends on the point, right? Remember in the classical obstacle problem proof 2, when we had x naught, we had the quadratic polynomial centered around x naught, mod x minus x naught squared. So I have to do something similar. So this is behalf. Okay, fix this. So now corresponding to this x naught, define h to be equal to this del E of uj plus little alpha times mod x prime minus x naught prime square over n minus 1 minus xn square, xn square. Okay, x prime xn. And now let's look at this. So on the point on this set, which is in the thin part. Okay, so now what I do is the following. So suppose this function makes sense on the following set. So now my set A for the other one changes. So now my set A is the following. So this is the set where xn equals to cn, where gamma n, xn equals to minus gamma n, and suppose this is my coincidence set. On the coincidence set, but this coincidence set is different from this coincidence set, okay? But nevertheless, it is a domain which has a slit, which could be rough at the local level. So it just could be that on this, you have something like this. I mean, it could be much more wilder than this, which I will show it cannot happen, but for the time being, it could be very wide. But the original U0, it was more like flat, which I don't have in this situation. So nevertheless, I don't have the ability to draw great pictures, okay? So I will just keep it as it is. This is the coincidence set of gamma, okay? So on this set, H is on this set, this quantity is 0, xn is 0, and this is positive, right? So on this set, H is bigger than or equal to 0. On the boundary far away, okay, on the boundary far away, you have that x prime minus x naught square over n minus 1 is very large, and if this cn gamma n is very small, okay, gamma n is very small, I can make that this is also bigger than or equal to 0. Why? Because then this would be a quantity which will be bigger than 2 epsilon, which will win over this minus epsilon. Right? Agreed? So del E of uj would at most be minus epsilon. This I can somehow readjust it by shifting this little bit and then adjusting my epsilon, going back and adjusting, doing a little bit of engineering. Okay? But if this is small compared to this, then I can always sort of make this 2 epsilon if I choose my epsilon small enough. Okay? And then I can adjust this. So H will be bigger than or equal to 0 here and here. And on this part of the boundary, I have that this is bigger than or equal to some. This is bigger than or equal to some Cn. And now if I choose alpha small enough compared to xn, because this xn is at most gamma n, if alpha is small enough, then I can still ensure that H is bigger than or equal to 0 if alpha is small. Therefore, to retain the positivity, it is harmonic inside, right? This is harmonic and this is harmonic. In the complement of this set, this set, this set, this set, and this set, I have to have that. This would imply that H of x naught has to be also bigger than or equal to 0. And at x naught, this quantity vanishes. So therefore, this will tell me that del E of uj is bigger than or equal to 0 for all E in this cone, in this tangential cone. This is exactly giving you the cone of monotonicity, right? Now, all of these things worked out more simply because I am using larger tools of monotonicity formulas, okay, which were not applied right away in the setting of classical obstacle problem. And if you see the development of the subject, the singular sets were understood much later in 1998. So it's for a large number of times, several geometric ideas with monotonicity formulas and other things have been been used in these problems, okay? But the hard part is to understand what is the right monotone quantity. So anyhow, so once I have this, and uj is just like rescaled u. So if I select my j0 to be large, that is r small enough, okay, I go back and I get that for my, because the coincidence set of uj in B1 is the same as the coincidence set of u in BRJ, right? So now I fix a j0 for which that epsilon is reached, okay? So now I sort of fix my j0 over there, clear? So therefore what I get is the following, that I have this and I have this, and this is the free boundary. Because I have a cone of monotonicity, like in the obstacle problem, I have that, I can touch it by cone. So this will give me that gamma u is gamma of 3 by 2 is Lipschitz. And then now I have to upgrade it to C1 alpha. For that, I need the following slit version of the boundary Harnack inequality. So suppose I have this situation and this slit, okay, such that this is given by xn prime equals to g of x double prime, where g is Lipschitz. So let's call this set a certain name, okay? So let's call this set to be some slit. This is my slit in Rn, such that Laplacian u equals to 0, Laplacian v equals to 0, and u and v are bigger than equal to 0, okay? Such that u and v are equal to 0 on the slit. Then the boundary Harnack. So now the thing is that just look at it this way, okay? So if I have this slit, and just drawing the picture, now you see that there is an issue. How you approach the slit. You can approach the slit from above or below, or in this picture from left or right. Okay? And then you can manage to have two different Dirichlet values. So at least in this situation, the first word that I kind of uttered in my boundary Harnack lecture was Martin boundary. That came from the abstract constant in SQ coordinate theorem. These names are also sufficiently abstract for me, at least for my taste. So nevertheless, but the thing is that you see that from that, the ideal boundary, which is the Martin boundary, the potential theoretic boundary, has this slit divided into two parts, from above and below. So therefore, in order to have a similar boundary Harnack principle, what I furthermore assume is that because I evenly reflect, I also assume that u and v are symmetric. So that I sort of get rid of that confusion. Okay. Then if they're symmetric, they vanish on the slit, then u by v is held there. Over here, you may think that you have to prove a new boundary Harnack principle for the slit, but actually not. And that is because there is a bi-Lipschitz transformation which maps it to a flat space with bounded where it solves an elliptic equation with bounded measurable coefficients, to which the Caffarelli phase Mortola falsa theory applies, which was for divergence Ax flattening, which is what I did. Remember? Although I did for Laplacian and Lipschitz domain, when I flatten, it doesn't really differentiate between one bounded, so one elliptic operator goes to another elliptic operator. The change in ellipticity is only dictated by the norm of this bi-Lipschitz transformation, right? Nothing else. So how do I do it? So here is what I do. First I start with this. Which way I don't know. Okay. First I start with this, which is xn minus 1 equals to g of x double prime. First I move it, I don't change the xn variable, I flatten it, okay, by this transformation. After the first flattening, it gives me exactly the picture of u0, the picture of the zero set of u0, which is, okay. So now the thing is that, at least if I fix now x double prime, and I just bother about the xn and xn minus 1 projection, in that projection, the picture looks like this slit. If I fix the other variables, so all across, I have a plane which is in x double prime. So this is like a split in R2, right? Now the natural temptation would be to open up the slit. So if you open up the slit, you want to take something like square root of xn minus 1 plus I xn. But then you will lose the Lipschitz character, right? So you write it in polar coordinates. So when you take square root, all these angles open up, right? And they go back to the upper half region. That is a bad choice. So instead of taking rho to the half, I theta by 2, that is what square root does, where theta and rho are in the xn minus 1 and xn coordinates, you take rho and I theta to the half. So this is the change that you do. So that retains the Lipschitz character. And so therefore, there is a bi-Lipschitz transformation that maps it to exactly this region with a uniformly elliptic operator. And therefore, now you can apply the boundary Harnack principle to these del E's, okay? And so therefore, u by v is now C alpha for this boundary Harnack problem. Now, how do I apply it to my original one? Well, the same thing, right? Now you know that there is a cone of monotonicity over here, which is C delta, which I happily kind of got rid of because all these things were true for all E which belong to a cone of delta around En minus 1. And now when I apply, if I argue the same way using the implicit differentiation of the boundary, implicit function theorem, I mean, what did I do? I just do it to xn minus 1, sorry, x double prime and g of, what is it called? G of x prime 0, I put it as 0, and then I just take ue, u of x double prime plus u of xn minus 1, gx double prime equals to 0. So gx, so the gradient of g is roughly gradient of minus gradient of x double prime u divided by u xn minus 1. Divided by, well, multiplied with u xn minus 1. Yeah, divided by u xn minus 1. Okay, and now how this quantity is not monotone, but then again I write it in this delta times ei double prime plus en minus 1, and then I am able to show that u of delta e double prime plus en minus 1 over en minus 1. This is monotone because the cone of monotonicity after a change of coordinates around the en minus 1 direction. This is C alpha, but when I open it out, this is delta of u e double prime over u e n minus 1 plus 1 is in C alpha. So this delta is kind of now fixed. So this is in C alpha. So if I go back, then this gradient of the graph is in C alpha. So gamma is in sigma alpha. And now even in this context, there is this very major higher order boundary Harnack principle developed in the slit, again by De Silva and Savin, that gives you right away up to C infinity by bootstrap argument. I will not even try to describe that, but there is a different argument which is based on adaptation of Nirenberg's autograph transform that gives you real analyticity of this regular part, which is due to Wen Wei Shi, Ashok Petrosian, and Herbert Koch. That is also a very major paper in this subject. And now regarding the singular set, it was studied much before this high regularity of the regular part of the free boundary. These were obtained around the same time in 2014 by these set of people, these two competing groups of people, so to speak. But the singular part of the free boundary, where this coincidence set has zero density, was studied back in 2009 by Petrosian and Garofalo, which is for the half Laplacian, and for generalists by Garofalo and Rossauton, okay, where you have the similar x and a problem with the thin obstacle conditions, okay, where the Neumann derivative gets replaced by the weighted Neumann derivative, okay. So all these things are there. There are many other works, and there is also a work of Figali, Rossauton, and Barrios, which shows that if I now take only strictly superharmonic obstacle, then there are only regular points 3/2 and singular points 2. So that is all the points that you can have on the free boundary. So that gives you a lot of non-degeneracy, okay, from below. If you have a strictly superharmonic obstacle, then by barrier considerations, you can show that u is bigger than equal to the same non-degeneracy estimate. But of course, not as easy as the or. I'm not saying when the other one is easy. That's a very bad thing to say, but it requires a little bit more work in comparison to that. And what else? There are many other results. There are results by Fogarty and Spadaro, which says that the other frequencies happen in very small numbers, not that often. Okay. And there are many other results, and this is a kind of an ever-growing field, okay, where a lot of smart people are involved. Caffarelli, Silvestre, Salsa. So the general A version of the problem, when A is not equal to 0, that is S is not equal to half, was studied by Caffarelli, Salsa, and Silvestre, where they got the same result, okay. And many and also some parabolic versions of the problems were studied, and there are like ever-growing results in these fields, okay. So it's hard to sort of, and also a different approach based on an energy-based approach to the regularity of the free boundary, okay, which is based on Weiss's epiperimetric approach for the classical obstacle problems that I didn't mention before, was also taken up in this context by Garofalo, Petrosian, and Mariana, where they were able to show that even these homogeneous blobs converges. Okay, so singular points are hard to study because if you just take these, and in fact, in the work of Garofalo and Petrosian, they show that a point is singular, that is defined as the zero set having the coincidence set having zero density, n-1 density. That is the same as having that the frequency is an even integer. So that was the first major characterization in that work. And then to study the singular points, they had to take u of Rx by r to the kappa. Because as I said, if you just take this, you cannot get that, even if these limits are continuous across the singular points, but the homogeneous limits need not. Because as I said, these two discontinuities can make up a continuity. So, I mean, this is a very competitive field. Of course, a lot of work has been done, but a lot of understanding is yet to be done, okay? And this is definitely one of the very mainstream subjects where thanks to Luis Caffarelli and Athanasopoulos, a lot of these developments in very recent times have happened and are continuously happening. So you see, so I mean, if some of you are interested, so what I will say is that, so this will be the end of my discussion on obstacle problems and thin obstacle problems. So this is all that I had to say about Caffarelli's contribution to free boundary problems that are part of my lectures. Harish tomorrow is going to talk about a different problem, which is a Bernoulli problem, a one-phase problem. And as I said, that Caffarelli, even in his, and that was done with Alt and also Friedman back in the 80s. Okay, so that one in particular, you see, like was so that one in particular was also inspired by similar theory of minimal surfaces. So what did I say? In the context of minimal surfaces, a major step that allowed to get full regularity of minimal surfaces up to dimension 7 was flat implies Lipschitz. Flat implies C1 alpha. So what Caffarelli showed, even in the context of these one-phase problems that Harish will describe, that Lipschitz implies C1, that flat implies C1 alpha. Okay. So so tomorrow's one, which so I will try to switch my lecture with Harish's, okay, so that he has his last lecture, because as you understand, free boundary theory is a very exhaustive lecture, right? And it's like trying to compile a lot of material all into one. I cannot do it quickly, because if I do it quickly, you just understand the math, but just understanding the math is like understanding next to nothing, okay? So in all point of view, I would try to defend whatever Harsh said, that no, whatever I did in my first lecture was perfectly justified. And without that understanding, the understanding of this is far from complete. Well, you can just understand them and line by line. But in order to get working on these problems, you need a certain intuition that has to be built a certain way. And okay, so maybe this sounds more like I'm reprimanding, which I'm not. I'm just joking, but not completely as well.